Yeah, good morning. Thanks for coming. It's a great pleasure. I mean, thanks for the introduction. It's a great pleasure and honor being here. In particular, because I'm from the Max Planck Institute, we're devoted to fundamental science, and I guess here is more application. What I can promise, however, so I'm talking more about fundamentals, but what I can promise is that I'm going towards nano. In fact, I think that wetting, which I'm going to talk about, is to a large degree a nanoscience, and this is one of the overall themes in my talk. Now let's see where do I have this. Let me start by introducing those people who did the actual work and thank them, which is, I mean, a number of people over the years. So there are group leaders like Doris Vollmer, Werner Steffen, Michael Kappel, Rüdiger Berger, Stefan Weber. Then there are former PhD students, Max Paven, Florian Geier. Nan Gao left meanwhile for Britain. He used to be a postdoc, is lecturer there. San-Yuk is now in Korea, professor. Then we have Clarissa Schönecker. She's at Kaiserslautern University, Professor Pericles, back in Greece, professor. Then we have Xu Deng, back in China, Professor Frank Schellenberger, still looking for a position after his PhD. Maria is still with us, and John is back to the States. I missed, maybe I don't. So these are the people who did the work. I just networked, motivated, did some theory. Now, Wolfgang Pauli, you probably know, is credited by saying that God made the bulk while surface was invented by the devil. I guess many of you can agree to this. If this is true, and if we then talk about wetting, so the simple situation depicted here, liquid in contact with a solid and a gas, this is a real nightmare. Because you have three interfaces, but in addition you have qualitative union with this contact line. So if the interface is complicated, contact lines are even more complex and difficult. And that's something we are realizing gradually. So wetting is often determined by what happens close to the contact line from the atomic range to, I would say, 100 or few hundred nanometer. Now you might wonder why, because if you think about wetting, then in textbooks you will find, I mean, this equation here, which is attributed to Young, which is based on the experience that if you take a surface and if you place a liquid drop, then if you take the same material on the surface and it's flat and smooth and you place the same liquid, then roughly you get the same something like, which is called the contact angle, so the angle between the solid liquid and the gas vapor interface. So that is something which experience tells us, at least roughly. If you do the thermodynamics, then you'll find that this contact angle is in a very simple way related to the interfacial tension. So to the interfacial tension of the liquid and the interfacial energy solid liquid and free solid interface. So this is what you find in textbooks, and this is basically what all science about wetting is kind of rotating around. And this is certainly true for thermodynamic global equilibrium. So if your system is in equilibrium, then this is it. Unfortunately, you cannot even measure precisely this equilibrium contact angle. So if you measure contact angles, it is something in the range between an advancing and a receding contact angle, but there is no way of measuring the equilibrium contact angle without, let's say, certain assumptions, which is a pretty bad situation. I mean, thinking about this is one of the Young equation, one of the fundamental equations in surface science, but there are two things which you cannot measure. Now, there is the advancing contact angle, so if you increase the volume of the liquid or if you push the drop, then at some point it will advance. And that's one limit, and this is called the advancing contact angle. And then there's the receding contact angle, so if you decrease the amount of liquid or if you push the drop away from the solid surface, then at some point the contact line will move, and this happens at the receding part. And any contact angle you measure of a sessile drop is somewhere in between, and people call it the static contact angle. Now, this wouldn't be so bad if the range is small, but typically the range is like 20 to 30 degrees at least. So even on very smooth materials, you will not get below 10 degrees, I would say. So the range is huge, and you cannot measure the equilibrium contact angle. That's kind of nasty. So this is one way of measuring it. You take a drop, you put it on a tilted plane, and you wait just before it slides down, you measure advancing and receding on the front side and on the rear side. This is how it's done. And this is also kind of depicting where contact angle difference may become relevant. In fact, the larger the difference between the advancing and the receding contact angle, the more the drop resists to sliding. So if you, for instance, think about drops on a windscreen or on glasses, then you would think, oh, this is really nasty. Not only it spoils all our theory, contact angle hysteresis, but it also, I mean, would be nice to have these drops just sliding down and you have a clear view. However, if you think about all those things where wetting is important, I mean, all those phenomena in life and in industry, which are kind of, I mean, this is a collection, then you'll find that for many of these applications, it's really desirable to have a drop not sliding. So if you think, for instance, about printing or painting, coating, bringing out of herbicides, insecticides, all these applications, you can go through the list. In most of these cases, the absolute contact angle may be relevant, but what is even more relevant is the difference between the two. Coming back to this situation, I mean, it's a nuisance that we cannot determine the equilibrium contact angle and cannot make use of Young's equation as we would like to do. But reality and in nature, the difference between the two, between these two contact angles is probably even more difficult than the equilibrium contact angle in itself. So the contact angle hysteresis is essential, and it's not just a nuisance, and it's essential for our life and all, I mean, those things surrounding us. Maybe I should just, let's go one more slide and compare it to friction. So the contact angle hysteresis is providing something to drops, which friction provides to solid surfaces. I guess you all remember in school, or many of us had this boring experiment, where you place a solid block on a flat surface, and then you start pulling on the block until it starts sliding. So that's depicted here. So there's a surface. In this case, we start sliding the surface. The block is attached to a spring. So you slide, you pull, and until there's a certain force, and this is depicted here. So there's a force, here's time. You start pulling, and at some point, the block starts moving. And then the force decreases and comes into equilibrium. And this is one of these, I mean, 300-year-old friction experiments. Again, I guess you would agree that this is relevant for everyday life. Without friction, life would be very different. But there is a difference also between the static friction and the kinetic friction. This is what, I mean, these electronic braking systems in cars are based on, so that you use this path and don't get into sliding. And we did the same experiment with a drop, because there are many similarities between, let's say, sessile drops sitting on a surface and solids. So that's Dominic Pilat during his PhD in Nangao as a postdoc, did a very simple experiment. He took a flat surface, placed a drop, and kept the drop with a capillary spring in position. And you start pulling on the surface, and at some point the drop starts sliding, and we measure the force with this micro capillary. The result is, and this is what we expect, so there's a force, here is time, and then you start increasing, you start pulling with the drop, but at some point the drop starts sliding, and this is determined by the advancing and the receding contact angle. So that's what theory says. And then we did the experiment, and I must admit I was even ashamed doing such a simple experiment. So this is here the drop, this is the solid surface, which we move in this direction here, and here's the micropipette. This green thing is only a reference. And then if we start sliding, you can see now the drop is still moving with the surface. Now the drop starts sliding and is in an equilibrium position. And you can see that the micropipette is deflected. And from the deflection of the micropipette, we measure the force. So it's conceptually as simple as this. Though I should warn you, it took a year for a very talented student to make this reliably working. But the concept is pretty simple. So a very simple experiment. The outcome is plotted here. So we have the force, and we have the time, and like in solid friction, you see an increase until the drop starts sliding, and then you see a decrease again. So even for those drops in these very simple experiments, they don't behave as we expect them. There is a static lateral adhesion or friction, and there's a dynamic part. So even there we need to distinguish between two kind of advancing and receding contact angles, but I don't want to focus on this subtle difference. What I want to, let's say, bring around is contact angle hysteresis is important, and without contact angle hysteresis, we would have a problem with friction. And just to give you an impression of what happens, and we see this every day in the lab, you know, just the simple task, you have a surface, place a drop on top. Sounds very simple. Here I have a surface which is, as I'm going to discuss later on, superhydrophobic. And they have a very small contact angle hysteresis. And placing, I'll pass this around. Oops. And so you could try yourself placing a drop and keeping the drop in balance, just to get a feeling of what happens when contact angle hysteresis is low. And this is not even close to zero, it's just low. In case there's too much water around, there's something to dry. And please be careful a bit so that you don't spill too much on your neighbor. Maybe I can pass it here. I need this thing back because I borrowed it from the hotel. So, just to get you an impression of what the world would be if friction between liquid drops and solids is low, and this is not close to zero. So, and let me the last general remark on wetting. I started out with the ideal, let's call it ideal surface. Ideal, this is textbook, and I must confess even our own textbook basically stops here. So the ideal surface, Young equation, things are in thermodynamic equilibrium, global equilibrium, then we can use Young's equation. In fact, we don't need any nano here. It doesn't really matter what happens close to the contact line. Young's equation is valid irrespective of the details close to the contact line or macroscopic. Unfortunately, there's something like contact angle hysteresis, dynamics of contact angle, all these things. So there's the difference between the two, and then you need nanoscale, because all these deviations happen close to the contact line, and we don't really know what is happening there. The main problem, I would say right now, is that there's no way of looking with a resolution of 100 nanometer or better to what happens at the contact line. There's just no method of looking at it. Microscopy, optical microscopy is quite good, but I mean, resolution is few hundred nanometers, and that's not good enough. So we are really lacking methods to understand more closely what's happening in this range between the advancing and the receding contact angle. People know why there is hysteresis. There are some reasons like roughness heterogeneity have been studied for 100 years. Right now the focus is more on adaptation, deformation, charging. Fernando is one of those people who knows best about this. So it's still an active matter of research and will be a matter of research for a long time. So now let's focus a bit on what the title was about. Nanostructuring surfaces to control wetting. Though we don't really know what happens at the nanoscale, we can still make structures and see how this influences wetting. Now I would like to determine wetting by making a specific surface, and in particular nanostructuring it. I'm looking at repellency because making surfaces liquid-loving is easier, particularly if you don't have water. I mean, you can make oils easily spread, so that's not a real challenge. Making liquid-repellent surfaces is more challenging. Let me start with water. I take a flat surface, place water on top, and even if this is a fluorinated surface, the contact angle is something like 120 degrees. Maybe 125, but not much larger. And it cannot be for fundamental reasons. Of course, we know there are situations where if you place a drop, contact angles are much higher. So a Lotus leaf is one example. Here is another example. I mean, the birds or feathers of birds, or if you look at the fur of mammals. I mean, the birds clearly rely on the fact that the feathers don't get wet. It's completely essential. I mean, if they get soaked, they cool down and would freeze to death very fast, and they can't fly. So they depend on super-liquid-repellency, not only water birds. People studied this effect of very high contact angles, we call superhydrophobicity. And the first artificial surfaces, at least which I know, are from Robert Wenzel, and he took paper and coated it with a fatty acid or with acids, organic acids. And he observed already contact angles of 170 degrees, so very high contact angles, almost a sphere, rolling off easily. And he already speculated, this is probably due to roughness. So flat surfaces don't have high contact angles. If you make rough surfaces, they do. So he already had the idea that this roughness quantitatively was not suitable for this situation. Quantitatively, Cassie and Baxter came up with the right idea. And the right idea they had was that obviously the situation is not that the liquid or the water is in direct contact with the solid, but the surface is structured in a way that underneath the drop you have some air. So basically, even underneath the drop you have an air liquid interface rather than having a solid liquid interface. And that's still, the main effect. You need to make a surface with protrusions, and the protrusions need to keep the liquid away from the substrate. Now this is, we can have a look at the Lotus leaf now with the electron microscope, and then you see these protrusions sitting on top of the Lotus leaf, and you clearly see this is a kind of wax, so that the drops are probably sitting on top of those guys here and then roll off easily. So the idea of Cassie and Baxter is conceptually definitely right. And here's the standard model system. So when people study superhydrophobicity, then they like model systems where you can do calculations. And so this is from David Curet's group. They have these micropillars, which are a few microns in size. And the idea then is, after hydrophobizing them, the water drop, if you place them on top, will only touch the top faces, but it will not reach the substrate. So that's the idea. The effect, by the way, it's not due to pressure, not to hydrodynamic pressure, it's capillarity, so the same effect which holds the drop in place. The drop is kept at this position and it's not falling down because surface tension is keeping it up. And the same happens in the case of superhydrophobicity. Water is sitting on top of these pillars and the surface tension is kind of keeping it up. So there's a vertical component of the surface tension which prevents the water from touching down. If you press on the water, so if you apply a high hydrostatic pressure, at some point you will exceed this angle of, let's say, 120 degrees and water will slide down. But as long as you don't, things are fine. And then you get surfaces which show a very low adhesion to water, and this is basically the essential, not the contact angle. Essential is the adhesion. So the adhesion between a water drop and the solid surface, and this is a superhydrophobic surface, is extremely low. And you can see that when the drop starts vibrating by adding a little bit of additional water, then it easily detaches here from the substrate. So it's really low adhesion, and you can, it easily rolls off. So a very nice example of low adhesion. Now, let's be more quantitative. What is superhydrophobicity? So it's a matter of definition, of course. And then if you look into textbooks, you'll find that, if the people define superhydrophobicity, there are two things. One is the advancing contact angle is supposed to be above 150 degrees. So that's here. And the second is if you tilt the plate, then water is supposed to run down by, if the tilt angle exceeds, let's say, 10 degrees. You need to specify the volume of water, but that's easily done. So this is the two criteria you find in text or in reviews. Unfortunately, it's very difficult to measure the contact angles above 150 degrees. It's simply, if you place a drop and you have to keep it in horizontal and you have to clearly watch around the surface, you easily make an error in tilting and all these things. So it's very tricky. In fact, we started out doing quantitative experiments when, in the discussion with students, they reported, I made a surface 160 degrees plus minus 5. And I complained, why are your errors so large? You have plus minus 5, while if you look at the literature, it's plus minus 1, or if you do normal contact angles, plus minus 1. And they said, this is impossible to do better. And we discussed, back and forth, and I complained, and they said, but it's not possible. But then they persuaded me that it's not possible to measure contact angles, if they're very high, much more precisely. And you find it even in the literature. So it's very difficult to use this criterion because it's difficult to measure. Adhesion experiments, by the way, are much nicer. So you could do the simple experiment like the drop jumping up and down. You could take a drop, bring it into contact with the surface, pull it back, and measure the force required to pull it back. Much more sensitive, much better. And here is an example from Robin Raas. So he developed a device. I think that's even commercial. So he took a drop, brought it into contact with a superhydrophobic surface, pulled it off, and measured the force. And when pulling back, and from the force, you can calculate the contact angle, and this is a very sensitive way of characterizing these surfaces. By the way, they already go for the receding contact angle. For adhesion, the receding contact angle is important, not the advancing. This is a nice way. But not very simple. You need a special device, and the forces are low, and it's not simple to run, not as easy as a contact measuring device. So we were looking also for other ways of characterizing superhydrophobic surfaces. And one we found by, I wouldn't say coincidence, but we found an easy one when asking a completely different question. The question we asked was, how does a drop advance and recede on such a structured surface? So what happens at the front of a drop and what happens at the rear? And we used the method which is, I mean, probably the one with the best resolution you can get. That's the confocal microscope. So we look with the confocal microscope from below, and we look underneath the drop what is going to happening. And we used as a standard sample one of those microstructured micro-pillar surfaces, like David Carré did, like many people do. So there's these micro-pillars. They are a few microns in size and a few 10 micron space. Place the water drop on top, and you look with a confocal microscope from below. And let me start with, so this is the situation here. We have the water drop now moving in this direction, and we look at the front side. This is the confocal image. In fact, we don't use any fluorescent labels. Confocal microscopy is made to image fluorescent things. We use the reflected light. So there is no fluorescence here. What happens is the light, which is usually used to excite fluorophores, is also reflected at so this is glass, at the glass-air interface, and that's shining yellow. These are the micropillars, but this is not a true optical image. We placed them artificially because optically this doesn't look attractive, so we replaced the pillars by these green squares. So that's not true optical image. What is again true is this yellow line here, which is the bottom side of the drop. And again, light is reflected when you go from air to liquid. This is why you get this reflection from underneath here. So this is the water drop, this is air. Now maybe difficult to see, but there's also some yellow light coming up here. And of course the reflection here is higher than up here, because if you have a planar surface, then more light is reflected as if it's tilted. When you tilt, then most of the light is going away. But I hope you still can see the front of the drop. So now let me try starting this movie, and then we watch from below with the confocal microscope at what's happening. Does it move? Yeah. And then you can see something not really dramatic. So what you can see is that this is gradually coming down, and it's basically touching one pillar after the other. So now this guy is establishing contact, then this one. Now this one is coming down, making contact, and so on. So this is like a wheel rolling over a surface, or a caterpillar. Not very impressive. It's a completely smooth process. This, however, is kind of contradicting on what you expect. I mean, you expect a defined angle, and there should be some kind of an instability. I mean, what's the contact angle here? The contact angle is 180 degrees. So in reality, all these superhydrophobic surfaces have a contact angle of 180 degrees on the advancing side. So advancement is a touchdown. And if you really want to define any contact angle at all, then it's 180 degrees. And all the discussion about, IF 150, IF 160 is kind of useless, because in reality, that's more a measuring artifact. And in reality, the contact angle is high. In fact, if you look in the literature, then Bartel, Chuck Ekstrand, and McCarthy kind of predicted this already. I mean, they studied superhydrophobic surfaces to some degree, and they predicted this. Now let's look at the receding side, because also there they expect a smooth process. So let's look at the receding side. Now this may be, can we easily turn down the light a bit on that side? Because, okay, because there you should still see some yellow light coming from the rear side of the drop. It's very weak. You will see it better when it moves or when it jumps. So that's not so bad if you don't see it now. Now let's get this moving. Okay, now we're looking at the rear side. So we are looking at here, and there's supposed to be one of the interfaces. And at some point, when starting to move, what happens? This is coming up and up and up and up. And at some point, it jumps to the next pillar. Again, the interface is coming up, so the angle becomes smaller and smaller. And at some point, it just jumps to the next one. So in the sense of being more dramatic, this is certainly the more dramatic situation, because there's a clear instability. There's a certain point where the contact here between liquid and the drop ruptures, and that's an instability, and it happens at a specific angle. Or let's at least finish this one and then. Yeah, good.
Question?
Sure.
Does the result depend on the pattern of the glass, the size between the...
Yeah. Mm-hmm. It depends on the number of pillars. Let's say same chemistry, then it depends on the number and on the density of pillars. Because if you have a large spacing, then very few pillars have to support all the rear of the drop, while if you have them narrowly spaced, the force is distributed over many pillars, and then they rupture later. So that depends on the specific structure. So here's, and this is basically kind of easy to answer your question here. So we plotted the angle versus time, and you see this decreases, and then there's a point where it can't keep the drop anymore, and it jumps to the next pillar. Decreases, jumps to the next pillar, and so on. And this kind of angle, which we call, obviously the receding contact angle, depends on the specific structure of your surface. So the apparent receding contact angle is defined and characteristic. So let me conclude. So the first conclusion is the traditional convention that you report the advancing contact angle and the tilt angle is not really useful, because this is so difficult to measure in 180 degrees in most cases anyways. So don't use this, rather use the receding contact angle. First, it's only one number, you need only one number to characterize the surface, and second, it's easier to measure because the angle is larger. Now for the next few slides, let me already make the conclusion now. What I'd like to persuade you during the next few slides is that if we talk about superliquid repellent structures, they should be as small as possible. Again, a very simple conclusion. So to make superliquid repellent surfaces, structures should be as small as possible. And the question is the following. Let's first start with a simple thought experiment. Place a water drop on a solid surface. Let's say you are supposed to make it as repellent as possible. So you start making pillars, you remove material underneath. So that's already good. The apparent contact angle increases. This is even better because there's much more air-water interface. At some point, however, this will happen. The drop will impale the structure and all your nice wetting properties are gone. And this already shows that making a high apparent contact angle is not the whole story. You need to combine it with a high or with a significant impalement pressure. So high contact angle here, but do not remove so much material that it impales the structure. And these are two conditions which are sometimes contradicting in design. So it's not sufficient to just fulfill one. So then continue this question. Let's assume we have again our micro pillar because it's the most simple one. What kind of length scale would you choose, or which kind of pattern? So let's assume you are given the task, make a surface which is as hydrophobic or liquid repellent as possible. You are able to vary the radius of these cylinders and the spacing. Which one would you choose? You could start with, this one is supposed to be here. You could decrease the size of the pillar but increase their number. You could get the idea of keeping the number and decreasing the size. And of course, you can do all mixtures. To me, at least, this was not obvious which one to choose. So we did a calculation. We did the simple calculation. So we only have two parameters. That's still very simple. We changed the spacing here in micron, so this spacing here, and we changed the radius. So this is the whole parameter space. In reality, you can only use this part here, because here, the cylinders would touch each other, so that doesn't work for geometric reasons. But you still have a huge space available. You can choose any one you want. Which do you choose? So first condition, you want an apparent contact angle high enough. So let's assume higher than 150 degrees. Then you can choose any pair of spacings and radii down here. So condition is you need to be below this line. Second, you want a high impalement pressure. So high impalement pressure, and we only talk about 3 kilopascal, which is not much. So if you want to keep this thing stable above 3 kilopascal, you need to be above this line, which then leaves this as the available space. And the precise numbers may be wrong by a factor of 2, but the trend is, I think, okay. And it clearly says that the structures you should design should be as small as possible. The smaller you get, the more availability you have. You definitely need to be spacings below 10 microns. And I think this is also true for all liquid repellent structures. Go as small as possible. And I think this is valid down to at least 10 nanometers. Of course, we can't make these structures, but at least that's a guideline. So superhydrophobic structures should be as small as possible. I should mention Chuck Ekstrand had a similar idea already 10 years ago. We just made it more quantitative. Now let's get back to the lotus leaf. This is a bit surprising. If you look at the lotus leaf, and this is now a lotus leaf from our botanical garden, at least the electron microscope images are from our botanic, and you see these structures, but those are micron structures. So this is 20 micron spacing, which is not very good. But then if you look more closely, you will see that the surface of those protrusions is covered with these nanoscopic structures. So nature had realized that they need small structures. They made this kind of compromise, and you may ask, why do they have then the microstructures? This should be sufficient. It's probably not sufficient for mechanical damage, because you also want to prevent mechanical damage. One reason of having those protrusions here, there are other reasons as well, is that, you know, if you damage this thing, if you put something on top, you may damage the top plates of these micro protrusions, but underneath you still have an intact surface. So the real challenge for making superliquid repellent surfaces is to combine all those things: high contact angle, high impalement pressure, and mechanical robustness. And this is by far not trivial and definitely not solved. If you also want good optical properties, then things become even more challenging. Good, now let's go from water, which has been done a lot, and water is easy because of the high surface tension, to oil. And you know that superhydrophobic surfaces are not resistant to oil. I mean, like the feathers of birds, immediately spilled by oil. So there's no way. The reason is that oil has a lower surface tension, and so if you place it on any surface, flat, homogeneous surface, it will form a small contact angle. Definitely not above 90 degrees, and water is always above 90 degrees. So rather than making pillars, what you need to do is structures which have an overhang. And that's, of course, more difficult. I mean, making structures which have an overhang rather than just 90-degree flanks is more tricky. And this was realized by Stefan Herminghaus, for example, and practically then realized by McKinley, Rob McCone, and these people. Now that's of course more demanding. And what people have done, examples are shown here. There's, for example, these tabletops done lithographically. Electrospun fibers work as well, although not as good. So the idea is, if you have a fiber, then the liquid can hang from the fiber, which partially works. Nanofilaments are much better. They are done by the Seeger group in Zurich. We have these suit-templated surfaces which work nicely. There's this Korean group making these tabletops with one or two more overhanging structures. And then recently we saw that these liquid flame spray structures are also very good for making oleophobic surfaces. Currently we use those three, depending on what we need: better wetting properties, higher impalement pressure, or more mechanical resistance, and what is easier available. So there's now a number of ways of measuring oil repellent surfaces. Now let me talk briefly about few possible applications, or what this could be good for. This is one example. So this is Volker Mailänder, Susanne Schöttler von Katharina Landfester's group in Mainz. And we tested what blood does to such superoleophobic surfaces. So this is a metal basket, so metal grid, which we coated with one of those things. And then Volker took his blood, poured it inside, and we stored it for 24 hours at 37 degrees. And afterwards, you could just take the basket and pour it out, and all the blood came off, leaving even no detectable protein behind, which I think is pretty remarkable. So they're really liquid repellent, these surfaces. Another example, and this is the textile, I passed around. So this is a normal polyester fabric which we bought in a department store. And we coated it with these nanofilaments. With these nanofilaments, so you can see the fibers which are coated with nanofilaments, nicely liquid repellent. And we use them for gas membranes. I guess one of those big challenges, over for the life of mankind, is that at some point we need to recapture CO2, at least when energy is produced. And one idea is to use membranes where the CO2 can pass into a liquid which absorbs and enriches the CO2, so that in a later stage it can be taken out and stored. And this is done with these ethanolamines. And such membranes are not wide-scale used, but this is one of the ideas which is around. So we thought we could make super amphiphobic membranes and maybe help improving efficiency or longevity, prevent biofilm formation, all these things. So these membranes, as you saw, at least for water, they are very liquid repellent, also mechanically stable, so you could step on them. We can make the test afterwards. And they keep their liquid repellency. And then Florian Geier did a test with CO2 exchange. And then even in the first experiment, he shows that the CO2 absorption through our very simple textiles is more efficient than on commercial membranes. I mean, this should not be overinterpreted because the geometries are different of all these membranes. But if in the first trial the efficiency is already higher, that's at least promising and stimulating to continue in this direction. So such things may be used for gas membranes because they can keep open pores with a higher stability than traditional membranes. That's one possible application. Now the last few minutes I'd like to spend on discussing a bit what we call microparticle factory. We're not that far. We talk about making supraparticles or particles with a size of 50 micron to 2 millimeter. And the idea is, why can't we use the substrate to make materials? So, for example, if you take, I mean, this is now not making materials, it's a simple first try. You take a powder of a polymer, place it on top, you heat, and then you form spherical particles just by surface tension. So this is trivial, and we can heat these surfaces up to 350 degrees. Just to show you an example, oops. So this is here first a lump of polystyrene, which we just heated up to 160 degrees. Polystyrene melts and it forms a spherical particle. So not very spectacular. If you tilt the surface, the particle comes rolling off. And you have a spherical polystyrene particle rather than a heap of powder. Okay, that's not so impressive, but then you can add complexity. You could, for instance, mix the polystyrene with some iron oxide. And while heating, you can apply a magnetic field, and you get magnetic particles. And to demonstrate this, there's the next movie. So here are two particles. And you can see this one is rotating. There is a magnetic field rotating around this petri dish, and they are floating at the air-water interface. And this particle was made when there was an external field when heating, when making the supraparticle, while this was made without a B field when applying heat. So you can say we can make these magnetic particles. So you can add some degree of complexity. Again, this is just playing around. And don't complain, I mean, these look dirty, but we artificially added some dirt because if you have a sphere which is rotating, that's not so impressive. So we added some dirt that you can see it's really rotating. Let me go a little bit more systematically. So your speculation could be, you could take, for instance, two liquids, let them react on the surface, and after, for example, applying temperature, UV light, vapor, whatever, you can then collect these particles. So you could really make particles. Maybe you can use them for chromatography, because you could make porous particles. For catalysis, it could be something like replacement for spray drying. Of course, not on the huge scale. I mean, we cannot make tons of particles. On the other hand, this is a very defined process which you can keep for longer. You can vary conditions. You can even change conditions while the process. For pharmacy, let me also mention the work of Manos from Portugal. They used it to make capsules and encapsulate individual cells inside. So they used super-amphiphobic surfaces to make these capsules which have then cells inside. So there are various things you could think about. But let me go a bit more systematically and first start with a simple making of supraparticles. Supraparticle is a big particle consisting of small particles. So you could have the idea of taking a dispersion, placing it on a superhydrophobic or super-amphiphobic surface, evaporate the liquid, and you end up with the supraparticle. You could, of course, mix and do all these things. Now, we were not the first to have this idea. This is from Orlin Velev's group in 2008. They used superhydrophobic surfaces, put a dispersion of 1 micron polystyrene particles, let the water evaporate, and then you can see this opalescent supraparticle. If you add gold nanoparticles, the optical properties change. You can play all these things. This is from Michael Grazielski's group. You can also make these donut-shaped thingies from Detlef Lohse's group, where you have these crystals on the surface and you can study in detail the structure of the surface. So many people working in the field. We thought the advantage of these superoleophobic surfaces, of course, that you can easily remove the particles afterwards. So these fundamental studies are fundamental studies, but if you want to produce something, you need to remove it in a permanent way. And then these super-amphiphobic surfaces are quite suitable. You can also, you don't rely on pure water as a solvent. You can also use surfactants, or you can use organic liquids. So we went in this direction, and then one of those things we did together with Shuji Fuji from Osaka, he had polymer particles which had these surface groups which are pH sensitive. And then when you let them evaporate, you place a dispersion on the surface, you let the water evaporate, you'll find that at pH 3, they form these nice crystalline supraparticles. They do so because at pH 3, this is positively charged. There's electrostatic repulsion, so all these particles have nice time to find crystalline packing. While if you do this at pH 10, then there's an amorphous amorphous structure, because then there's only van der Waals attraction as soon as these particles see they easily attract each other. So you can control structure. Sang-Hyuk Wo, he was interested in titanium dioxide because that's photocatalytically active. So he wanted to make porous supraparticles out of titanium dioxide. So he evaporated his dispersion, ended up with these particles here. Looked like this. So this is the supraparticle, let's say 200 microns, and I mean you can see that the structure inside is pretty porous. This is photocatalytically active. So he did the following experiment. He filled in a Teflon tube with these supraparticles, because they're easy to handle, you just pour it inside. And then he had a reactant flowing through, and he shined some UV light. And then, I mean, for the simplicity, he used rhodamine, because you can see this is nicely orange, and when it passes, after passing, I mean, this photocatalytic reaction chamber, it's completely decomposed, and the solution is transparent. And you can verify that it's really photocatalysis. I mean, there's a clear experiment. So you can make photocatalytically active particles. And we thought, how could we improve catalytic activity? Well, it's the immediate next step. Then we should make the supraparticles more porous, so that reactants and adducts can flow in and out more easily. So we thought, well, this is easy. We just mix our, for example, catalytically active small green particles with some polymer particles. We form the supraparticle. Then we apply some heat and burn away the polymer. And then we have all these holes from the polymer, and it's much more porous. Now we started doing this 2 years ago, and for some time without much success. And then, fortunately, at some meeting, I met Arash Niko Bashman from the physics department, and he said, "Oh, I can simulate the process." So he simulated the evaporation of a droplet of a binary dispersion, and then he predicted that there must be stratification in the sense that the small particles should end up at the surface of the supraparticles and the big ones more in the center. I still don't have an intuitive explanation why this is the case, but there's a chemical potential gradient which leads to the fact that small particles should enrich the outside and the big ones should go more to the center. And it's one of the few cases then when Dong Liu did the experiment in our lab, where the experiment immediately brought the theoretical prediction. Also, Arash needs to admit it's the first time that this came out so nicely. So you can see all these small particles, and this is a mixture of polystyrene particles, now small ones, 0.3 micron, and big ones, 1.4 micron. We mix them at a volume ratio 1:1, let the drop evaporate, and then we immediately found that the small particles enrich at the surface of the supraparticle, and in the center is a mix still of the big and the small ones, but clearly the concentration of the big ones is higher here, while it's completely, you form a crust of the small particles. And if you look carefully, I mean, this is now an electron microscope cross-section through half of one of these supraparticles, and here you can see the enrichment of the small ones, while this is, let's say, more homogeneous mix in the inside. Then based on these results with simulations, of course, it's easy to find conditions where you get a complete mix of particles. Basically, you just evaporate fast, or you add some ethanol and do play these tricks. And then we can make now porous particles. So this is one example. So here is the surface image. Here is the inner image of titanium dioxide nanoparticles mixed with polystyrene, but the polystyrene particles have already been burned away. And you can see this high porosity of these particles, which had been made primarily with polystyrene. So now we can adjust porosity at least to some degree. Good. But this is, I mean, if this ends up in anything we can use at all, I would be happy. It's one direction at least we are following, and I think it's promising, but I don't know where this is going to end up. These are only the first steps. But I think you can make more complex particles in a very defined way. We're working on making many particles at the same time. And with this, let's say, possible application, I'd like to conclude. So I started out by talking about the advancing and receding contact angles and how important they are. Second, they are linked to the nanoscale. If you want to understand advancing receding, you're automatically at wetting at the nanoscale. Then with respect to the superliquid repellent surfaces, I hope I persuaded you that using the receding contact angle to characterize these surfaces is appropriate way. If we think about superliquid repellent surfaces, the challenge is to combine high contact angle with mechanical robustness and high impalement pressure. Single one of them is easy, all three is very difficult. And then I presented one example of, what you can do with, if you understand wetting, what kind of things you can do with it, like making supraparticles. With this, I'd like to thank first those organizations which made all these experiments possible, which is the German Research Society, of course, the Max Planck Society, the European Union with this ERC grant, with an ITN, and the Humboldt Foundation. And I'd like to thank you for your attention. Thanks a lot. You mean, let's say a polymer solution, for example. Yeah, we did some experiments, and this works just as nicely as before if we use our, we mainly tested our super-amphiphobic surfaces. They work perfectly, no problem at all. I'm not sure what about these super-hydrophobic surfaces. The issue is always then, do the polymers absorb to the surface and change the wetting properties? Not in the immediate first second, but if there's a chance that the polymers, for example, absorb to the surface, things may change. On our super-amphiphobic surfaces, I'm pretty optimistic they will work, no problem. Klar.
Thank you for a very nice talk. I was wondering if you use a very hydrophobic, immiscible, viscous oil on the surface, which is flat, and you put a drop of water. Is then the receding and the transient angle, is it really identical? Because it's molecularly moving or something, so there's no trapping or sticking?
Basically never. Not even on our surfaces or in general?
Well, in general, if you have a water on oil surface, you have no defects, I think, no pinning.
Yes, that's true. And this is also, so if you have basically a liquid on a liquid, then contact angle is, on a liquid it's 0. Because, the experiment is of course difficult, but if you could turn a liquid surface, then a liquid oil lens would slide down, clearly. There are these slippery liquid infused surfaces now, where you try to keep a liquid close to a surface by having a rough surface, fill the rough surface, for example, with oil, place a water drop on top, and then the water is basically sitting on oil. That drastically reduces the contact angle difference, but you still have a difference. Yep.
So as you were looking at the receding contact angle, it looked like there were two deep pinning events in quicksand.
Yes.
One on the front edge and one on the back
Yep.
edge. And so what did those angles look like relative to one another? And did we see that in the...
So that's the one tricky part. The tricky part is where do you measure the receding contact, the apparent receding contact angle at all? And we measured it, let's say, 10 microns away from the surface. So there, you wouldn't see the small transition close to the micropillar. What happened there is, there is still, on the microscopic, the liquid surface is still in thermodynamic equilibrium, so following Laplace equation. Which means the curvature remains constant. And at some point, there is a transition between two configurations. So it forms, in one case, you have a micropillar and this kind of connection, and that changes shape. There is a phase transition between two shapes. That's true. But it's purely, let's say, a question of Laplace and combining the positive pressure, cylindrical pressure in this direction, and the negative curvature in the other direction.
Does that disappear if you use a hybrid structure where you have a micropillar covered with the nanopillars like the Lotus?
It should still be there unless it detaches much earlier. If you make a hybrid structure, which is, the hierarchical structures is the way to go, definitely for also mechanical strength, then even the, let's say, I think you wouldn't be able to detect it because then even the small contact angle on the top face of the micropillars is so low that it will detach so early that probably you won't see it. I don't know though, we didn't do the experiment.
Maybe back.
Oh, okay. Yeah. During your presentation, you mentioned that you're using confocal microscopy to sort of view sort of what's going on the surface. And I think at one point you said that sometimes you guys are limited by the resolution of confocal microscopy. microscopy. Now, have you guys ever thought of using some other technique like near-field scanning optical microscopy? And because I think the resolution for that is under 100 nanometers.
So I think we tried, so it's one of the issues in the whole group, always trying to look for optical methods. There are, of course, these high-resolution methods where you basically look at the position of individual fluorophores. This, however, requires that these stupid fluorophores sit at a specific position for a given time. Now, if you add fluorophores, that could work, but the fluorophores diffuse very fast. So you have to fix them. But if you fix them, dynamics is gone. And we are always, entangled in this kind of, then let's try to fix it, but then we get high resolution. And then you are right, we can get resolution much better than even 100 nanometer, but nothing is moving anymore because basically we're looking at a fixed structure. So this is after, I would say, 2.5 years a PhD, we kind of gave up on all these high resolution methods. There is still hope, still ways to improve it, but I don't think high resolution, at least not in those typical forms where you aim at positioning individual fluorophores, seems to work, unfortunately.
That's great. Thank you very much for a nice talk. And as you mentioned, the mechanical robustness is a very important point and factor from the viewpoint of the application. And you haven't talked about that the progress or your effort to have the higher mechanical robustness.
Mm-hmm.
Do you have any idea to increase? Because the simultaneously you have to have the core structure in nanoscale core structure and mechanical robustness. It's very difficult to have both at the same time.
Yeah. In particular, if optics still comes into play. So there is one way. One way is to make hierarchical structures. So like, for instance, the textile. So the textile is extremely hydrophobic. If you step on it, for example, it still is hydrophobic. Probably you destroy the very top layer of the nanostructures, but you do not destroy the interior because that's mechanically protected. So I think making hierarchical structures, so having a big structure which is coated and supporting the mechanical strength is one way to go. The problem occurs if you don't want light scattering. So if you want a smooth, nice looking, like a car window. I mean, we could make it super hydrophobic, no problem, but it would scatter so much light you wouldn't be able to look through. So combining mechanical robustness with optical transparency, that would be nice. Because, I mean, automatically any protrusion needs to be a few hundred nanometers size, and then it's scattering light. So I didn't... Not very much. I know Receding is doing lots in this direction, but right now we didn't do systematically try to combine mechanics plus optics. Not yet.
So thank you for your talk. And my question was considering the size considerations for just a dry surface of pillars, you want the small spacing as well as.
Yep.
But for a liquid infused surface, do the considerations change? Considering you have lubricants.
This is not an easy question. It's tricky because on one hand, these slippery surfaces behave just like these ones. You just replace air with oil. And then all the formalism and all the arguments perfectly hold. It's not, because you always have the liquid meniscus around your drop pulling the other one down. So you always have, let's say, a zero force pressing your liquid down. And that changes the situation. So I cannot give a complete answer to this. I think this consideration will still hold, but it's less relevant because if you have the liquid infused surface, the fact that you have this infused liquid will dominate many properties, and the precise structure will not be so important anymore.
Concerning the difference between advancing and receding, as you advance, you are forming and rupturing interfaces. And if you have interfaces, you have charge separation. So the charging state in the advancing and receding are necessarily different.
Yeah, we could even almost do the practical experiment. So if I don't know where the water bottle is, if you do the same experiment on this plastic, which is perfectly insulating, you would probably see that the drop is sometimes hanging at a certain position. And it's hanging there because, these things are insulating, and one drop coming, when it leaves, deposit charges. And the next drop coming notices the charges and really likes to sit on the charges. So charging, and I think this is one of the real challenges. I mean, it's obvious on on many of these hydrophobic surfaces because they are very nicely insulating, and they charge enormously. The question is if even under normal conditions we separate charges, and to which degree charge separation contributes to contact angle hysteresis. It's not easy to notice so much because I mean, after a few milliseconds the charge may be gone, but it could still change the dynamics of wetting. So this is, I think, one of the big challenges.
Okay. Well, I think that we have not yet managed to measure it.
Yeah, right, right.
Charge transfer is pretty fast.
Yeah, right.
Okay.
Hmm?
Thank you for the extremely insightful talk. So I have one question regarding the confocal microscopy. So we actually are trying to image under-liquid droplet using confocal microscopy, but the challenge that we are facing is the numerical aperture of the objective is not
Yes.
to capture the bite.
Yep.
And we don't have an immerse lens, so the walking distance is also kind of a problem. So I want to ask what kind of optics do you use?
Depending on the type of question, I think. So we use both oil immersion or water immersion or the air objective, depending on what we are looking at.
So if you try to image a superhydrophobic surface, it's like
With these pillars, for example, I think they are made with air objectives because the main, let's say, the main region between what we are interested in, which is the drop, and the substrate is air. That, of course, doesn't fit the pillars. The pillars are glass or SU8. So there's always this compromise. So I'm pretty sure they tried both. And I think these images I showed were done with an air objective, but I'm not sure. This is one of those things which is constantly under discussion, which is.
Maybe we should have a discussion later on.
Yeah. And probably you would need to talk to Pericles or, I mean, those people who do the experiments. This is, like all these discussions are 20% I'm out because they are discussing, I mean, these details, and I know it's an issue. And one should keep in mind, many of these things are slightly distorted. So it could well be that, let's say, if I report a contact angle 140, it may be 142. I mean, the systematics is right. So in principle, there's one contact angle. But it could be distorted due to the fact that you always have light coming through air, partially something with a refractive index, which distorts the images. And this needs to be taken into account. Yeah.
Let's have a...
Yeah.